Greetings from Vignesh. Lab 2 Motion of Falling Objects. So, these were the assumptions made for the following work. Assumptions made were drop from rest, that is, the initial velocity is equal to 0. The forces acting on the body was assumed to be the gravitational force and drag force alone. Gravity is equal to minus mg, where the minus sign denotes the movement of the object is towards the down. The drag force equal to minus bv square. V square as per the given assignment. B is the drag force constant, and negative sign indicates the direction of the drag force is opposite to the direction of the velocity. So the net force acting on the body is not equal to 0 since the force is acting on it. I mean the gravity and drag force. So this is the tracker file. This is actually a ball dropped from a height. I have to rotate the video for user convenience. So this shows the video details such as frame rate, start frame, end frame, etc. So this is the calibration done, which was done by measuring the diameter of the ball. So this is the path traced by the ball. These coordinate points were used in future for comparison. This is the experimental model, and this is the case 1 for building the computational model. The only force acting on is assumed to be gravity. F is equal to minus mg. M is the mass. Even though the F depends on mass, during actual determination of velocity, F is independent of the mass. Let me explain. From Newton's second law, final velocity is equal to initial velocity plus net force, which is the gravitational force, into delta t divided by mass. So this mass gets cancelled with the gravity, the mass over there. So final velocity is independent of the mass. So moreover, the final position is equal to initial position plus the final velocity. So it's dependent only on the on the final velocity. So in term, final velocity does not depend on mass. So final position also does not depend upon mass. So this is the computational model which was built. So this is the mass of the ball. This is the initial position, and initial velocity of the ball was 0 as per the assumptions. So the gravity was assumed to be 9.8 meter per second square. This is the unit vector, and this is the while loop which was constructed for the model. So the weight force, the weight due to the force due to the weight was minus ball mass into gravity into j hat. So the net force was assumed to be only the gravitational force. So this is the same as in the earlier program. So this shows the graph on the ball falling. So this is a perfect parabolic shape. So coming to the case 2, the forces acting on the were assumed to be gravity as well as the drag force. So in addition to the gravitational force in the case 1, drag force was included in this case. So weight force is equal to minus mg, and newly included drag force is equal to minus bv square. Minus sign indicates the opposite direction to the velocity, and b is determined on various iterations made. So this is the computational model. So everything is same as it was in the earlier case. The only thing which was included here is the net force is equal to weight force plus drag force. Whereas the drag force was calculated using minus bv square. For determining v square, it was taken out of the vectorial format, and it was squared, and then it was put into the vectorial format. So because of which it because of squaring the velocity loses its negative signs. So after squaring, an additional negative sign was included so as the direction remains same. So this is squaring. So running the program, actually the blue arrow indicates the weight force, whereas the yellow arrow indicates the drag force. The weight force is a constant for the entire period of time, whereas the drag force increases as the ball proceeds, which says that the drag force is directly proportional to the velocity. So this is the comparison. This is the experimental coordinates. This were these were the coordinates obtained by considering weight alone. These were the coordinates obtained by considering weight as well as drag. So this is the comparison graph. So the blue line shows the experimental results with the dots. So there are few minimal errors. So red line shows with considering weight round, which is a perfect parabolic shape, whereas green is with weight and as well as drag, which is a slightly deviated parabolic shape. So comparing all these, it's evident that the experimental model is in fine agreement with the model created using weight as well as drag. So there were minimal errors at these 2 points, which might be because of the human error. So the experimental model is found to be in agreement with the model with weight as well as drag. So what if the object was initially thrown downward? Would the terminal velocity in this case be the same or different from the case whereas the same object was initially dropped from rest, which means Vi is not equal to 0. Let's see. So by changing the initial velocity of the ball, I have given it to be around minus 2.5. Let's see what happens. Running the module, use something like this. So we can easily predict that the drag force has some initial value, which means there is some initial velocity also. So this is the the results obtained in model. So this is no way. Let me conclude it last. What does it mean? The velocity was the same predicted by the model with and without drag. Which model predicts the terminal velocity? So let us see. Actually, I concluded it at the last. Let us see all the cases first. So running the module, this is actually the velocity graph, which is a perfect straight line. So this is the terminal velocity, minus 4.086. So this is considering the drag force. So this is also slightly deviated straight line, which shows that there's some amount of drag force towards the end. So this is the final velocity. So these were the comparisons of various things. So from the experimental model, considering the last two, the last two observations made, the final velocity was calculated to be around 4.02. So these two were the results obtained from the model. This is considering the weight alone, whereas this is considering both the weight as well as the drag. I'm sorry, it was found to be around 3 So it's clear that the experimental model is found to be in good agreement with the model including the weight as well as the drag. So let me come to the conclusion. So from the three graphs obtained, experimental, weight alone, weight plus drag, the model with net force equal to weight force plus drag force was found to be in good agreement with the experimental results, which was clearly evident. So from the what does it mean, the terminal velocity predicted using the model with drag force was closer to the experimental terminal velocity. And also from the what if analysis, the terminal velocity of the two cases, that is Vi equal to 0 and Vi not equal to 0, was not the same. So from almost everything, it's clearly evident that the drag force plays a very important role, because even from everything in almost first two cases, the drag force, the forces, the models from including the drag forces was found to be the accurate models. So I said thanks a lot.